Okay, so I think we're ready to go to the next session. So we're happy to have Tommy, who's going to talk about random unitaries in extremely low depths.
Cool. Hello, everyone. I'm Tommy. Yeah, and as Isaac mentioned, I'll be talking about random unitaries in quantum systems and how they can be formed in surprisingly low depths. So most of this talk will be based on this work that came out last summer with Jonas Haferkamp and Robert Huang. And I'll also, especially towards the end, sprinkle in a few details from some forthcoming follow-up works with a number of people, some talented grad students, Laura Sway and Dom Kufel, as well as Fermi Ma and Norm Yao, Fernando Brandao, and Robert. Cool. So just a roadmap of what I'll be talking about. I'll start by giving a kind of gradual and very broad introduction to random unitaries and why we care about them, just to get everyone on the same page. I'll then describe the main results of our work on how we can form them in very low depth. I'll try to give at least a little bit of intuition and mention some applications of our work. And then I'll discuss kind of two follow-up questions that often came up over the last year when we presented these results, which we resolve in these forthcoming works that I mentioned. Cool. So zooming way out, we're at a very exciting moment in quantum science where modern quantum experiments are increasingly large and coherent and allowing us to push the boundaries of traditional regimes in quantum physics and information and computation. And this progress has raised a lot of interesting questions, which many of us are here today trying to answer. So I've sprinkled just a few of these questions on the slide, which will be especially relevant to the content of this talk. So one question is, how do we benchmark large quantum states and dynamics? So we heard from Robert about some approaches to this in the last talk. Another question is just how do large quantum circuits and Hamiltonians behave? How can we find quantum advantages, especially in near-term experiments? And a question that'll be especially relevant to our results is what properties of quantum states or dynamics are easy to measure in quantum experiments, and what properties might be fundamentally hard to measure. And so these are all broad questions. They've been studied for a long time. And in these studies, there's been a surprisingly ubiquitous tool. And that is the notion of a Haar-random unitary matrix. So a random unitary on n qubits is just a 2 to the n by 2 to the n matrix drawn from the Haar measure, the uniform measure, on the unitary group of size 2 to the n. And so if you've never heard of these objects or studied them before, you might wonder why we ever care about such an operation. Aren't we normally interested in highly structured circuits on n qubits that maybe, factor some large integer we'd like to factor? Or maybe implement some simulation of some precise Hamiltonian that models, the behavior of phonons and electrons in nature? Why would we ever want to think about a completely random operation on my giant Hilbert space? And that's a good intuition to have. But nonetheless, over the last years or several decades, people have come up with a surprising number of reasons and different fields where we do care about these operations. And so I'd like to start this talk by just kind of running very briefly through like a large handful of these applications. Just to motivate the results that follow. And so I'll break these applications of random unitaries into several classes. And the first class is random unitaries as an application. So places where we actually want to apply a random unitary in a quantum experiment. And one of these examples, a very prominent one, is due to Robert and Richard Quinn and John, which is classical shadow tomography and fidelity estimation. And so in this work, they show a very surprising result, which is if I take a quantum system and I apply a random unitary to it, and then I'm measuring the computational basis, I can often learn many more properties about this system much more efficiently than if I just directly measured the state. Robert just told us about some recent works on how in special situations you don't need this random unitary, but I think in the most general case, we still think you do in some cases. A second case where we actually want to apply a random unitary in an experiment is in quantum supremacy experiments, such as random circuit sampling. And in particular, our best theoretical arguments for the classical hardness of random circuit sampling rely on the resemblance of random circuits to Haar random unitaries. And a final kind of still developing application of random unitaries is in quantum cryptography. And there's a lot of current work on how random unitaries could form the foundation of quantum crypto systems. A second class of applications of random unitaries is as a toy model. So this has been especially popular in quantum many-body dynamics, where we have lots of interesting Hamiltonians and circuits that we'd like to understand the behavior of. But studying these systems exactly is often very hard. And so we like to come up with toy models for them, which probably share similar universal features, but might be easier to study on numerics or analytically. And so, yeah, there's many examples of basically random circuits and random unitaries being useful toy models for various phenomena in many-body dynamics. Another area where random unitaries have been used as a toy model is in quantum machine learning and variational circuits, where a lot of the challenges in training variational circuits can be understood by appealing to the resemblance to random unitaries. And a final example of random unitaries as a toy model is in quantum gravity and the ADS-CFT correspondence, where it turns out lots of the sort of very naively surprising features of this correspondence can often be understood rather simply by just appealing to arguments about random unitaries in purely quantum systems. And so the final application I'd like to mention, which again will be prominent later on in this talk, is random unitaries as a counterexample. And this relates back to this earlier question about what properties of quantum states or dynamics are easy to measure in experiments and what properties are fundamentally hard. And it turns out that in our theoretical study of these kinds of questions, the most common way we prove that a property of a quantum system is fundamentally hard to learn is by considering a random example of a state with that property. And by considering some random example, we're typically considering very complex quantum states that are genuinely hard to learn. But then by assuming it is truly random, we can often appeal to analytic tools in the study of random unitaries and just random matrix analysis in mathematics to actually formally study and prove properties of these systems. So a huge amount of the recent developments in quantum learning, the kind of lower bounds, the proofs of hardness, a high number of them appeal to arguments about random states and unitaries. Cool. So hopefully we're all on board with the utility of studying random unitaries. And if we think about kind of all of these applications I just listed, there's one central question we should answer, which is in what circuit depth can a quantum circuit appear to be a Haar random unitary? So this is clearly important in applications. It controls, what depth, how many gates we need to apply to realize these operations. It's also important in their use as toy models. When do we expect these toy models to apply? To short time dynamics or only to very long time dynamics? And it's also, of course, useful in knowing where these quantum learning separations apply or kick in. And so if you just try very naively to answer this question, the answer looks kind of pessimistic because a true Haar random unitary with very, very high probability has exponential depth in the number of qubits. And the reason is very simple. It's simply that there's many more deep quantum circuits than shallow quantum circuits. So if I choose a random circuit, it's most likely to be very deep. And so, this appears kind of pessimistic because the states and unitaries we can realize or that we see in nature are not exponentially deep. They're typically, polynomial depth or lower depth operations. And so you might think that the study of Haar random unitaries does not apply to the states we see in nature. But really, if you think a bit more, all this tells us is that we need some notion of approximation when a state or unitary is not identically a Haar random unitary, but rather when it looks like one from some perspective that we care about. Yeah, people have come up with several notions of when a state or unitary, quote unquote, look Har random. And most of them are built on very kind of physical principles. So we consider ourselves as an observer performing some experiment that involves some unitary that we care about. So maybe I prepare some initial state, I apply a unitary drawn from some ensemble to it. Then I do some quantum circuit to that state. Then I apply another. It's okay, it's just going to confuse me. Maybe in the future. Then I apply another application of that unitary to it, then another circuit, and so on. Maybe I have some measurements in between any possible protocol. And I say a unitary looks Har random if me as an observer performing this experiment involving that unitary, if I cannot distinguish that unitary from a truly Har random behavior. So it's a very kind of physical notion of approximation. And to make this a little bit more formal, one notion of when something looks Har random is known as a unitary K design. So an ensemble of unitaries forms a unitary K design if it looks Har random in any experiment that queries the unitary up to K times. So where the number of applications of U in this experiment is up to K for some integer K. And I can do arbitrary circuits in between. So this is one popular notion. But in some of these applications I mentioned earlier, especially the ones in quantum learning, we'd like to take K to be very, very large. Like we'd like to prove that some properties are hard to learn in any polynomial time experiment. So for K growing as any polynomial in the number of qubits n. And so to capture these kind of very large K settings, people have come up with a new notion of approximation. This is more recent, known as a pseudo-random unitary. And we say that an ensemble of random unitaries is pseudo-random if it cannot be distinguished from the Har ensemble in any polynomial time quantum experiment. So any experiment that queries U any polynomial number of times. And also we make one more minor restriction that the quantum circuits we do in between are also polynomial depth or polynomial size quantum operations. So we're now considering, many, many applications of U, polynomial number of applications, and in exchange for this kind of big ask, we're also going to assume the quantum circuits are, only polynomial time, not completely arbitrary. And typically this study of pseudo-random states and unitaries, it's built off of kind of widely believed cryptographic assumptions. Yeah. It is, well, how should I say? It turns out that if you ask for something to be a K design for any polynomial K, there's a straightforward argument that this requires a depth that's bigger than any polynomial. And so what we do is we weaken the ask just a little bit. We ask for it to only look Har random if these quantum circuits in between are polynomial depth. And this then allows us to look Har random for any polynomial K, and for the ensembles we realize to be polynomial depth. Yeah. Yeah, and please, anyone just shout out questions as I go along. Cool. Yeah, actually, this is a good moment to pause. Are there any more questions on the motivations or definitions of K designs and pseudo-random unitaries? Cool. Okay. Okay, so we have these objects. We know what they are now. How easily can we realize them? So I want to just mention kind of the current state of the art as of roughly 1 year ago. So a kind of long line of works, starting back really in the 2000s and especially in the 2010s, a lot of more recent works, have studied when do local random circuits look like unitary K designs. So if I take my n qubits, and at every time step, I pair up nearest neighbor qubits, and I apply a Har random 2-qubit gate to that pair of qubits. And then I repeat this time step after time step, drawing new random gates at each time. There's been a whole long line of work studying how fast does this ensemble of unitaries converge to a unitary K-design? And the culmination of these works came from this paper with several authors last year, which proved that random circuits form unitary K-designs in a depth K times N, roughly, on any circuit geometry. So even in 1D circuits, in some depth K times N, random circuits converge to unitary K-designs. So what about PRUs? So these were a much more recently introduced concept, and most of our progress on PRUs comes from this pair of papers, again from last year. And the end result is that local quantum circuits, some highly structured circuit ensemble, but a quantum circuit ensemble that can be compiled in terms of 2-qubit gates. So local circuits can form pseudo-random unitaries in depth poly n in 1D systems and depth poly log n in all-to-all circuits. So this poly n depth in 1D systems is kind of similar to this unitary K-design result. It grows with some polynomial in the number of qubits. But then we have some slightly stronger results saying if we can do very long-range 2-qubit gates, we can get even lower circuit depths. And the precise circuit ensemble that they study and prove is a pseudo-random unitary is something called the PFC ensemble. It was introduced in this paper by Metger et al. Last year. And the details of it won't be terribly important for this talk, so feel free to ask after, but I kind of won't go into exactly what it is right now. But so they introduced it in this paper. They proved it had some sort of weak form of security, so it looked random only in some kind of simple subset of experiments. And then this result by Fermi Ma and Robert Wong strengthened this and said, no, this is really a PRU. It looks random in any polynomial time experiment. Yeah, the notion of locality is that every gate is still a 2-qubit gate. It just might be between two very distant qubits. Yeah. Cool. So I'd like to just remark that these circuit depths seem very intuitive and reasonable. So for example, 1D circuits require at least linear depth to generate high entanglement, or to have light cones that extend across the whole system size. These are clearly properties that a random unitary would have, and so it's not so crazy to maybe suspect that a unitary K-design or a PRU, something that looks random, would also need to have these properties and therefore require at least linear depth. And by similar arguments, one can actually prove that classical reversible circuits require linear depth in 1D to form pseudo-random classical circuits or a classical analog of designs. This follows from a very simple light cone argument. I can just explain it right now. Say I have some circuit ensemble, and I'd like to test whether it's low depth or whether it looks like a completely random classical circuit. So I just need to query the circuit with two different input bit strings. One, say, the all 0 bit string, and one, the same bit string, but with the leftmost qubit flipped. And now, by just a very simple light cone argument, if this circuit ensemble is low depth, the outputs of this circuit will be the same on all of the qubits outside the light cone of this first qubit, because these input bit strings were the same away from this first qubit. So any output bit that's outside the light cone of the first qubit also has to be the same. On the other hand, if this circuit was completely random, I would generate two completely random independent output bit strings. So they, with very high probability, would be different on all of their bits. And so with just this very simple argument, you can see that classical circuits require at least linear depth to form designs or pseudo-random circuits. And so now I'll tell you about how something very different happens in quantum systems. So I'll start by just kind of stating the main results of our paper, and then I'll describe the exact circuit ensembles we consider and give a brief sketch of how we prove these results. And please just interrupt with questions whenever. So our first main result is that random quantum circuits form unitary K designs in depth K times log n on any circuit geometry. So essentially replacing this k times n dependence in earlier results with k times log n. So exponentially shorter depth in the number of qubits n. And we also proved that this log n dependence is optimal. So you cannot do any better than this. For the experts, the notion of error we use in our unitary K designs is something called the relative or multiplicative error. I won't go into the definition. It involves kind of strange looking inequality symbols for quantum channels. But suffice it to say, it's a very strong notion of error, kind of the strongest one people normally have considered. And it is even a bit stronger than this kind of intuitive definition I gave earlier of whether I can distinguish the unitary from Haar. Roughly speaking, this multiplicative error implies that our unitaries look Haar random in any experiment that queries U and even can perform post-selection. So it's kind of a very powerful notion of error.
So is there by random quantum circuit, random quantum gates?
Yes. I'll be very explicit in a few slides, but yeah, it will be some precise circuit architecture, but each gate will be independently random 2-qubit gate. Okay, I'll just first now state our second main result, which is that certain structured ensembles of quantum circuits can form pseudo-random unitaries in depth poly log n in 1D circuits and poly log n in all-to-all connected circuits. So again, basically exponentially smaller depths in the number of qubits n compared to our previous knowledge. And so just to emphasize, the circuits we consider are very shallow. They have very low complexity, and they create only very short-range geometrically local entanglement. And yet we prove that they're indistinguishable from Haar random unitaries with exponential complexity. So how do we show this? So as you might guess, because we had these kind of 3 results in a row, all of which exponentially improve the n dependence, there's some very kind of simple and general framework we have for proving these results. And I call it building random unitaries brick by brick. And it's a pretty general approach to exponentially reducing the circuit depth of any random unitary. So the circuit ensemble we consider is drawn right here. It's as follows. So imagine I take my n qubits and I lay them out on a 1D line. And then let me break these qubits into patches as follows. So I'll take the first poly log n qubits and call that the first patch. And then I'll take another patch of roughly sized poly log n, and so on. Here, poly log n, you can think like log n squared or something. I'll be a little more explicit in the following slides. So I break my n qubits into sort of geometrically local patches of poly log n size each. And then in the first layer of my circuit, I apply a random unitary to each patch of qubits. So a random unitary U1 on the first patch, U3 on the second patch, U5, U7, and so on. That's the first layer of the circuit. And then in the second layer of my circuit, I do the same thing, but shifted by half a patch over. And so in this way, the whole circuit is connected. Every qubit kind of, way talks to every other. And then I stop. So I don't repeat this any further. I just consider this 2-layer ensemble. And we prove that this ensemble is indistinguishable from a Haar random unitary on all n qubits. So in a little more detail, our precise result on unitary designs is as follows. So imagine I set the size of these patches to be log n, in particular log nk over epsilon for some error epsilon. What we prove then is that if each small random unitary is drawn from an approximate k design on log n qubits, then the entire circuit forms a k design on all n qubits. And there is some small degradation in the error of the design during this process, but this turns out not to be very important for the end results. And so what you can imagine here is we already know that k designs can be formed by local random circuits in some depth that grows linearly in the number of qubits. So we know that random circuits on Xi equals log n qubits form designs in a depth that's order k times xc. Yeah.
So again, it's MBS of polynomial dimension, right? So there's no contradiction.
Yes.
There's no contradiction.
Sorry, contradiction with what?
But with having that long entanglement and design.
No, that's essentially a result of our work. Yeah, yeah. There are some, how should I say it? You can make arguments along these lines, like the ones you're trying to make in your head, that essentially prove that the depth you need grows as log 1 over epsilon. I'll talk about this a little more. If you consider like a swap test to detect the entanglement, you'll find that the depth you need grows as like log 1 over epsilon, but it does not impose a constraint on the n dependence, and it's only like a very weak constraint on the epsilon dependence. Yeah.
So even if the error is at 0,
Yeah.
the local thing, like you still get like epsilon that depends on the number of qubits in the block.
Sorry, what's the question? So if the input epsilon is 0?
Let's say the local thing is like exact K design.
Yeah.
Even so, you get like epsilon error depending on how large.
Yes. So yeah, which comes into this constraint. So you'll pick up some error from each individual term. You're supposing that's 0. And then you'll have some additional error, which is like n times n divided by 2 to the xc, where xc is the patch size. And so then if xc is at least log n over epsilon, 2 to the xc is like epsilon over n. And so the n dependence cancels and you get an epsilon out. Yeah, yeah. Yeah.
So your result shows the likelihood.
Yes. I'll talk much more about this. Yeah. Cool. So just to finish the argument on the depth, we know that random circuits form designs on xc qubits in depth k times xc. Here we're setting xc equals log n. And so we immediately get that we can form designs in depth k times log n. And this, builds upon these earlier works, which we kind of put into each small block. And then we get out a much bigger unitary on all the qubits. Yeah. Sorry, say the last part of that. Oh, if we iterate it, like, yeah, it's kind of, okay, if you just take this result and you apply it again, you'll find that you don't get anything better. And the reason is that the input to our theorem needed the error to be like epsilon over n, where n was the total size of the system. And so if you try to apply this again, you'll find that you need the errors in each individual design to be like 1 over n for our theorem to apply. But then all of our constructions of designs require log 1 over epsilon depth. So that log 1 over epsilon turns into a log n, and you'll find you get the same k times log n depth out. So this is as far as you can go. Yeah.
So this is an iteration of, I think, Isaac's question, but if you have an exact K design, like small use on C qubits, the circuit forms said like 1 over nk times like 2 to the C approximate K design on a qubit. So.
Okay, I can't do the math in my head, but let me just tell you the answer. So say each of these was Haar random. So it's a K design for any K. Then the output will form a K design with error epsilon for any K and epsilon such that C is greater than log K over epsilon.
Okay.
Yeah. Cool. Maybe just a very brief comment. In a follow-up work led by Laura Sway, a grad student at Caltech, we have since improved this to order K times log n for all-to-all connected circuits. So kind of paralleling this improved depth for PRUs in all-to-all connected circuits, we now see that this depth is also possible with designs. And for various reasons, it's required here to not consider local random circuits, but actually to consider some highly structured circuit ensemble, which we introduce in this work. Cool. So let's now turn to PRUs. And our construction is essentially the same. So our more detailed theorem on pure use is as follows. So if each small unitary in this ensemble is drawn from a pseudo-random unitary on poly log n qubits, then the entire circuit forms a pseudo-random unitary on all n qubits. And so you can again immediately see, if we know that pseudo-random unitaries can be formed in depth poly C in 1D from Robert and Fermi's earlier result, we now know that they can be formed in depth poly log n using this two-layer construction. And similar for the all-to-all case. Cool. So if there are any more questions on just the statement of our results, I'm happy to answer them. Otherwise, I'm going to turn and kind of give a sort of high level, but with a little bit of detail sketch of how we actually prove this. Cool. Okay, so our proof is actually very simple. It didn't start that way, but with some time honing it, we've got it to be actually very simple and short. And so this central idea in our proof is something we call the gluing lemma. And the gluing lemma states that if I take two random unitaries, so say a blue unitary drawn from a K design on these qubits, and a green unitary also drawn from a K design, and I apply them in sequence, and they overlap on at least a small logarithmic number of qubits, then the composition of these two unitaries is a K design on all of the qubits, with some additional error that decays exponentially in the number of qubits in the overlap. And so before I tell you how we show this lemma, I just want to remark that you can immediately see from this lemma how we prove our main result. So we essentially just consider this two-layer ensemble, and we apply the lemma order n times at each step, gluing the next random unitary into a design formed by all unitaries to its left. And this is very versatile. It extends to sort of any connected circuit geometry you could consider. Okay, so how do we prove this gluing lemma? I'm going to give a little bit of technical details here. This is the only really technical part of the talk. But just for the people who are interested, I thought it would be nice to flash the main ideas of the proof. So again, the proof is pretty short, and it's broken into 3 parts. Each part is like half a page long in the end. So the first part is kind of dry, and I won't go over it too much. But we prove a kind of short technical lemma for bounding the relative or multiplicative error of unitary designs. And this lemma mirrors a result from an early work by Brandau, Harrow, and Horodecki, but it improves their result by a factor of k factorial that will be useful in some of our applications. Our second step is not even to address anything specific to the gluing lemma, but just proving a much simpler approximate formula for the expectation value over a Haar random unitary. So for anyone who's studied Haar random unitaries, you'll likely have come across this formula. And this formula is the formula for what happens if we take some quantum state rho on k copies of our original n-qubit Hilbert space, and we twirl rho, we average it, over applying a random unitary in each of the k copies. So this formula, appears if you try to compute basically any observable property of a random unitary. And there's an extremely well-known formula for how to compute this expectation value in terms of permutation operators on the k copies of the Hilbert space. So here, sigma and tau are objects that take k copies of our Hilbert space and just permute them. So they'd move one copy here to here and one copy here to here, and so on. And there's a reason that these permutation operators appear. It's actually pretty intuitive. These turn out to be the only operators that commute with a random unitary operation. So to kind of see this, like if I take a unitary U and I apply it on all k copies of my system in parallel, this clearly commutes with a permutation operator. Because if I apply all the unitaries before the permutation and then I swap them, it was the same unitary on every system. So it's the same as if I apply k unitaries after the permutation. Yeah.
So number 1, do you need the relative error between the blue thing and the true error?
No, this is, yeah, that's a good, it's kind of, This is kind of a technical result where we say if you can bound the additive error on a certain simple input state, then this in turn bounds the relative error for any state. So no, it doesn't address the gluing at all. It's just kind of a useful method for bounding the relative error. Yeah. Cool. So this simple argument says that the permutation operators commute with a random unitary, and it turns out they're the only things that commute with it. So if I take some state rho and I average it over k copies of a random unitary, I'm basically projecting rho onto the span of the permutation operators. And in doing so, we get this formula where basically I compute the overlap of rho with some permutation operator sigma at the input, and then I spit out some permutation operator tau at the output. And this coefficient called the Weingarten matrix encodes the fact that the permutation operators are not perfectly orthogonal to one another. So we have to keep track of that when we're projecting onto their span. And it's very simple to derive this formula from yourself. Yeah, it's very easy. Cool. And so, this formula is extremely widely used in basically all works on random unitaries. And it's also kind of annoying. Like anyone who has worked with these Weingarten functions has probably been annoyed by them because they don't have explicit functional forms in most cases. They can be both positive and negative, which makes bounds involving them kind of tricky. And in general, they can be just a bit of a nuisance to work with. And so this second step of our proof is to show that at least for these kind of large patches of random unitaries that we consider, we can just forget about the Weingarten elements entirely. So in more detail, why is this true? So the key fact we use is that the permutation operators, they're not perfectly orthogonal to each other, but they are approximately orthogonal when they're acting on a large Hilbert space. And there's a very simple calculation you can do for yourself to see this. If I take the inner product of one permutation sigma with another permutation tau, you can kind of compute it as just a number of loops when sigma and tau are contracted with each other. And if they're the same permutation, then basically every leg in sigma will get inverted by tau for each of the legs. And so I'll get kind of k loops in this trace. And then I'll get that their overlap is 1 if they're the same. But then if they're a little bit different from each other, if they're say k minus 1 loops, then their overlap, you can see, will be 1 over 2 to the n. And if they're a little more different, if we have k minus 2 loops in this contraction, it'll be 1 over 2 to the n squared, and so on. And the simple point, which is all I want you to see, is that whenever they're not equal, this overlap is at least 1 over 2 to the n. So even if the permutations are very close to each other, if they're not the same, this overlap is exponentially small. And from this fact, we prove that we can basically just treat the overlap matrix of these permutations as the identity matrix. And that means if I'm projecting rho onto the span of the permutations, I just take its overlap with each permutation sigma, and I spit out the same permutation sigma. Cool. So this is a nice formula that greatly simplifies our life. The final step of our proof is just to apply these ideas to this specific product of unitaries in the gluing lemma. And with this kind of result from step 2, it's very simple to do this. We essentially just plug this formula in for the first, the blue unitary, and the second, the green unitary. This produces a sum over 2 permutations, sigma and sigma tilde. So sigma from the blue, sigma tilde from the green. And there's just one important piece in this formula I want you to note, which is when the output of the blue unitary, so some sigma acting on the region where they overlap, is contracted with the input, the sigma tilde, from the green unitary. So this produces a term like trace sigma, sigma tilde inverse. But now, from what I just told you, the permutations are approximately orthogonal to one another. And so this means that sigma should equal sigma tilde inverse to good approximation. And so we show that, and once they're equal, we just have the same permutation on all subsystems of our qubits. And this reproduces the formula for the Hartwirl on all of the qubits. So this is essentially the whole proof of the gluing lemma. And then from the gluing lemma, like I explained, we get our results on designs and PRUs. So the error, yeah. So there's lots of tildes here. The error in this first step is like k squared over 2 to the n. You can bound it kind of simply using this first result I have, this technique for bounding the error. The error in this step is like k squared over 2 to the number of qubits in B. So it's exponentially small in the overlap, which is what we show. Yeah, that it turns out easy. It just adds on. It's like very easy to include that. Yeah. So the total error we get in the end is just like the sum of the two input errors plus some additional term that's like k squared divided by 2 to the number of qubits in the overlap. Yeah.
Without the first one, like, do you get like k factorial factor here?
Yes. And it's not terrible if you're considering like 2 or 3 designs. But for these results on pseudo-random unitaries, it's absolutely essential to get rid of that. Yeah. Cool. Okay. Oh, yeah.
Sorry, very real question, but the last approximate sign, so.
Yeah.
Having a twirl like this implies that it's a good sign.
It implies what?
Implies that it's like I just have this kind of a twirl.
Yeah, because this, I see the confusion. Yes. Yes, I gave this kind of, these earlier definitions of K designs, they basically amount to proving that this twirl is the twirl of the K design is equal to the twirl over the Har up to some small error. And that is the same error that all of these curly equals are. Yeah, so basically like bounding any property of experiments that queries you always go through this formula. So if this formula is close, then any experimental observable is also close. Yeah. Sorry, what was the question? The minimum. So the error is like k squared over over 2 to the number of qubits in this support. And our theorem applies as long as that's less than 1. So you need the number of qubits to be greater than log k squared. Cool. So I'll now kind of very quickly go over just a little bit of intuition, touching on why these arguments about entanglement or light cones don't seem to apply, and then discuss some applications of our results. And then if there's a little time remaining, I'll discuss these more recent works. Okay, so just to address, the first thing, why do these arguments about entanglement and light cones seem to apply in classical circuits, but not in quantum? So we have this simple light cone-based argument for classical circuits showing that they can't look random until their light cones extend across the whole system, which requires linear depth in 1D. But now if you try to run this same argument from the classical circuit in the quantum case, so say we put in some all zero input state to our construction, and then put in, the same input state, but perturbed on 1 qubit, our results prove that the outputs of this are indistinguishable from 2 independent Har random states. So even though the inputs just locally differ on only 1 bit, the outputs just look like 2 completely different Har random states. And I don't have a full intuition for why this statement is true, other than just to try every method you could think of to distinguish these states and see that all of them fail in the same way. So one way we could try to do this is just to try measuring the light cone. So try seeing where these 2 input states differ on the output. And there are some works that give it very explicit protocols to do this. Even the latter one is implemented experimentally. But you'll find if you dig into these that all of these methods diverge exponentially in the size of the light cone. And so if we have a circuit that is just deeper than log n, the size of the light cone will be just bigger than log n. That means exponential of that light cone will be just bigger than any polynomial in n. Because e to the log n is a polynomial in n. So e to something that's bigger than log n is bigger than any polynomial in n. So all of these light cone-based schemes become super polynomially difficult as soon as the depth is just above log n.
Sorry. Are you saying that to measure the light cone of D, you need a e to the D circuit, like sample complexity?
Sample complexity, yeah.
Essentially, you're measuring entanglement.
Yeah, some form of it, yeah. You can also try to measure the entanglement directly, so that's the second bullet, by just doing a swap test on half the system, which gives you the purity of one side. But doing a swap test, essentially what you're measuring is like 2 to the minus in Renyi-2 entanglement entropy. And so again, the size of the observable that you're trying to resolve is decaying exponentially in the amount of entanglement. So as soon as the amount of entanglement is just bigger than log n, the complexity of seeing that entanglement is just bigger than any polynomial in n. And then finally, you can try a brute force approach of just learning the entire circuit. Then you'll also find that some very nice recent algorithms for learning shallow quantum circuits all blow up exponentially in the circuit depth. So again, once the circuit depth is above log n, these algorithms do not take super polynomial time. And so now we know why all of these things break down when they do. It's because after this depth, the output states are just truly indistinguishable from hard random. Cool. So I'll now, yeah.
So you mentioned that classically you always need a extent for pseudo random
Yeah.
classical
Yeah.
circuit. Quantum you don't.
Yes. You want like a
Right.
Y?
What is more? Is there anything very fundamental?
I think
Or just
yeah. So here's my wishy-washy intuition, is that we have non-commuting observables in quantum systems. And so in a classical system, like say you want to hide information about these input bits, you're kind of limited by how much you can hide it, because I can always kind of resolve all the information in my state with just a z-basis measurement at the end. Whereas quantum systems have like a new way to appear random, where I don't just kind of scramble my information, but I scramble it into things that don't commute with each other. And so then if you measure in the wrong measurement basis, then you see very little information about my state. And so, yeah, my best intuition is that quantum systems are able to hide information in things that don't commute with each other. And if we do this in a very random way, then it's very hard for me as an observer who knows nothing about this state to figure out where that information is hid.
Okay. Let me ask you about the complexity, hidden complexity, the compare the classical and the quantum fields.
Uh-huh.
How about the hidden complexity?
What is the hidden complexity?
You have the K, overlap between two layers. And then you get some kind of complexity compared to the classical case and the quantum case, there would be some difference. In the viewpoint, the advantage in the quantum case. And do you have some hint or some kind of idea of the hidden complexity from the quantum side?
I think you would need to explain to me more what hidden complexity is. Maybe we can discuss right after. Yeah, I'm not sure right away.
I think that in the viewpoint of the geometry, there seems to be literally a gap on this kind of the hidden complexity. But still, I don't know whether between what is the advantage of the classical and the quantum. I don't know, but I think that you guys are expert on understand approach on the viewpoint of the entropy coming from the complexity. In that point, I ask you about.
Yeah, let's talk after. Yeah.
So can I just summarize your intuition as because of the non-competitivity, information still propagates by the Robinson bound.
Yeah.
Randomness, I guess some sort of randomness can propagate in a very non-local way due to non-competitivity.
I think so. This is the part where my intuition breaks down a little. So you can ask, like, can we distinguish like these two input states from each other? And my intuition kind of gives some plausible reason for why we can't. But then our results prove that lots of features of the output distributions of these states like exactly resemble the Haar case in a way that like this simple non-commutativity argument does not show. So I think there's lots of features of our results that are not explained by this simple argument, but it gives you some feeling why the quantum systems can look random much faster than classical. When we prove this log n lower bound, we use exactly this intuition I described. So it's a way to prove they need at least this depth to appear random, but I don't think it really explains why like all of their moments look exactly Haar random at this depth.
So to distinguish like input A, input B, you need to only examine the first 4 qubits in principle. But to the non-commutativity, this randomness is somehow propagated to all the other qubits, and that's how things become.
Yeah, or it's more like it's not actually, it's 4 qubits here, but it's actually like polylog n qubits. And that's a really big Hilbert space. That's a super polynomially big Hilbert space. So you can't do like brute force tomography and stuff on just that light cone. That's the intuition. Yeah, Tibor?
I guess third case here would be some kind of classical stochastic circuit.
Yeah. I think it becomes difficult to say what you mean by like a completely random stochastical circuit, a stochastic classical circuit. Like, is it a circuit that takes any input state to maximally mixed, or is it? I'll tell you some smaller facts after, maybe. Yeah, to some extent, some features of the quantum case appear there too. Cool. I'll go a little bit faster through the remaining. I'll first just mention some super immediate applications of these results. And then I'll describe in a little more depth some like broader applications that are drawn on these more recent works. So I mentioned all these places where random unitaries appear, all these applications. And to some extent, our results have implications for each of these areas, as you might expect. So one kind of prominent and hopefully useful one, Robert mentioned this, is that in classical shadow tomography, you don't need a truly random Clifford circuit on n qubits. You can get away with a log n depth Clifford circuit. So we need a lot less experimental resources for classical shadows. Another application is proving properties of the output distributions of random circuits and random circuit sampling. So in particular, we can prove that all of the constant moments of the output distribution match those of what you would get from a Haar random unitary, which is known as the Porter-Thomas distribution. So all of these appear at log depth, we now know. Also in things like variational circuits, it implies that barren plateaus set in very early at just above log depth. And there's essentially nothing you can do to get around that besides, okay, this motivates more structured circuit ansatz for variational circuits. And in quantum learning, a lot of the learning advantages that we used to think only applied to Haar random unitaries in very complex states, we now know apply to very low complexity states as well. And so in the remainder of the talk, I want to kind of dig in a little bit more to 2 further applications, which we kind of more fully explored in 2 follow-up works that will be coming out soon. I'll discuss them one at a time, and I'll be a little bit brief just for the sake of time, and feel free to ask me more afterwards. Okay, so the first implication I want to discuss concerns quantum information scrambling. So we've talked about this a little bit already, but for some of us in the room, we're very used to thinking about random unitaries as toy models for quantum information scrambling, where scrambling means the spreading of local quantum information into non-local degrees of freedom on the entire system. And there's a whole host of quantities that we care about in information scrambling. So things like the decay of OTOCs signifies that local information has become very non-local. This in turn connects to things like Hayden-Preskel recovery, where we can recover information scrambled by a unitary with access to only a few of its output qubits. and even more nuanced measures of information scrambling like higher point OTOCs or operator size distributions. And all of these phenomena just manifestly require very large circuit depths because their definition is essentially that information on one input state has spread even to very far away qubits. So what gives? Why have we been thinking of all of these quantities with random unitaries and random circuits as a toy model? But now we've proven some result that random circuits look Haar random at such low depths. And maybe just to give a little bit of intuition before I tell you the reason, you'll notice that in any experimental protocol to probe any of these quantities, we always need to apply time reversal. So for example, in OTOCs, we first scramble our information with some unitary, we then perturb it, and then we backwards time evolve to refocus that information for some simple measurement. And in this Hayden-Preskel recovery, we first scramble our information with some unitary, but then if you look at the efficient decoding protocols that exist, they use the inverse of this unitary to recover it. And similar for higher point OTOCs and size distributions. And so what our results really prove is that quantum experiments with the ability to reverse time to perform both U and U dagger can detect features of quantum dynamics that are exponentially hard to detect without time reversal. And this is why we can form random unitaries under our definitions of designs and PRUs in such low depth, because those definitions essentially only capture experiments with just forward time evolution and not more powerful experiments with both forward and backwards evolution. And so in a sort of forthcoming work, we introduce a new notion of unitary designs and PRUs that also captures this ability to perform backwards evolution. So if you care about some experimental scenario or observable that involves both forward and backwards evolution, you shouldn't be thinking about standard unitary designs. And we introduce a very straightforward definition that would capture these experiments as well. And then from this definition, we prove some sort of basic properties that conform with our expectations. So we prove that in 1D circuits, you can form these strong unitary designs in linear depth. And in more non-locally connected circuit architectures, we prove that you can do even better. So you can get these strong unitary designs in order k times poly log n depth.
So what do you mean by strong? Even with time reversal, you cannot distinguish this?
Yeah, so this unitary looks Haar random in any experiment that queries U at most k times and U dagger at most k times. So
U dagger contains like entire layer, only the last layer.
U dagger, so I give you some circuit ensemble. There's some unitary you draw from that ensemble. U dagger is just the inverse of that entire unitary. Yeah. Yeah, sorry, I'm going a little fast because I was low on time, but yeah. And so this, this pair of results, linear depth in 1D and log depth in all-to-all, sort of conform much more to our intuitions. And so I think this kind of, in some ways, completes our picture of unitary designs under standard definitions, which are extremely well suited to any experiment that just involves U. We can get everything looking Haar random in log depth. For more powerful experiments with U and U dagger, we need linear depth in 1D and log depth in all-to-all. We develop, actually some substantially new proof techniques to prove this result about log depth in all-to-all systems, which I can describe more after. Let me just get to the end because I'm only a few slides away. Cool. So a second follow-up question, and I just want to flash some results here. So another natural follow-up question is, what about symmetries? So the dynamics and states we see in the real world are often, not completely unconstrained. They might be constrained by some symmetry principle that, the system must obey. And so what happens in that case? Can we still realize really random behavior very quickly? Or can symmetries somehow constrain the ability of quantum systems to look random? And so in a different forthcoming work, we address this. And we prove that for any discrete on-site symmetry group, essentially all of the results I just told you about low-depth random unitaries go through. So we consider the same two-layer circuit, but where each small unitary is either a symmetric unitary design or a symmetric pseudo-random unitary. So something that's indistinguishable from a Haar random unitary that respects the symmetry operation. And we prove that this low-depth circuit cannot be distinguished from a symmetric Haar random unitary on all n qubits. It's known actually for continuous symmetries that this is not possible by very simple arguments. So Zhongwan Ha has a recent paper on that. We can also, I can just mention, we can also extend this into circuits with translation invariance, considering the circuit ensemble here. And so why do these results matter? Well, I think they have kind of interesting implications for one particular question, which is what is the complexity of recognizing the phase of matter of a quantum state? So say I'm an experimentalist or some observer, and I have access to many copies of some quantum state psi, and I'd like to determine what phase of matter psi is in. So maybe I'm guaranteed it's either in the trivial phase or a symmetry breaking phase, and I'd like to perform some measurements to determine which is the case. And so there's kind of a whole host of recent works, including by Isaac and Ethan, who are here, studying this question and proving some rigorous results on the complexity of this. And our results kind of pour a bit of cold water on this in some sense. So our previous theorem on low-depth symmetric random unitaries just immediately implies that recognizing whether a quantum state is in any phase of matter, trivial, symmetry breaking, SPT, topological, etc., is quantum computationally hard as soon as the correlation length of that state is just bigger than log n, so growing pretty weakly in the system size. And the reason this is true is I can take some random example of a state in any phase by just considering the fixed point state of that phase and applying a shallow symmetric circuit to that fixed point. And then our results that I showed on the previous slide prove that under some widely believed quantum cryptographic assumptions, this output state cannot be distinguished from a completely random symmetric state. And so this proves that for any definition of phases of matter, where the phase of matter of a quantum state is invariant under a local shallow symmetric circuit, the phase of matter cannot be learned once the correlation length is at least this big. And this complements, I should say, existing phase recognition algorithms, which have runtimes largely growing exponentially in the correlation length C. So for very short range correlations, like constant with respect to the system size or log with respect to the system size, you can learn these phases in polynomial time, which these works show. And when C is just growing a little bit bigger than that, just above log with the system size, it becomes super polynomially hard. Yeah.
So maybe, I don't know whether similar, but so you can think of a Tor code and perturb, and then perturb it by, whose effect is same as radically changing the parent Hamiltonian by some XZ field.
Yeah.
And if the correlation lengths go above certain size.
Yeah.
I mean, I guess it's not proven, but by just still measuring the original same local stabilizer, whether such a state, unless for very fine-tuned trajectory, whether such a state the logical information can be faintly decoded or not is, I think, still not resolved. Using this argument, do you think maybe you can just state that actually it's impossible?
I think it's tricky, and I think my next slide is on this actually. It's tricky to know whether we should believe any of these results for the states we see in the real world. Let me just let me describe a little more intuition on why I'm not sure whether the states we're constructing in our theorem are representative of, say, the toric code with a field that tunes you, closer to the critical point. Okay, so like as you just described, we might be interested in the real world. We have some model Hamiltonian. We tune it close to its critical point. How easy is it to learn the phase there? And that state has some correlation length that could be greater than log n because we're moving close to the critical point. Does that mean that as soon as that correlation length is above log n, that it's hard to determine that phase for some specific Hamiltonian and ground state? So to gain more intuition about this, let's dig into what kind of states are appearing in this counterexample that yields our theorem. So let's consider even the simplest possible phase of matter, a symmetry breaking state. So the simplest example of a ground state that features symmetry breaking order would just be the GHZ state. So a superposition of the all up state and the all down state. And this is the ground state of just the Ising Hamiltonian with ZZ interactions. And so if we didn't apply any circuit to this, we just looked at the bare GHZ state, it's very easy to see that it has symmetry breaking order. We just detect some long range correlations in the Z basis, where if this qubit is in the up state, then any distant qubit is also in the up state. And these long range correlations signify the presence of symmetry breaking order. So what happens in the states we consider when we take this GHZ state and we sort of scramble it under a low depth circuit? Well, what happens is these states still have genuine symmetry breaking order, but their order parameters have become highly random scrambled operators on roughly log n qubits.
Sorry, but here, are you assuming that pseudo-randoms break the symmetry?
No, everything respects the symmetry.
Everything respects the symmetry. Shouldn't this force? Oh, doesn't have to be. Never mind.
Yeah. Everything, every local gate respects the symmetry. Yeah. And so this output state, it still has long-range correlated order, but it's not between the Z observable here and a Z observable far away. It's some very complicated feature of roughly log n qubits here is correlated with some very complicated feature of roughly log n qubits on the other side of the system. And so if I knew the exact state, if I knew this shallow circuit I applied, I could very easily just measure these order parameters and verify that my state has genuine symmetry breaking order. But if I don't know this random unitary, so if I don't know enough about my state, then this order is super polynomially hard to learn.
If it's not a discrete but U1, then log n is not enough, so you can probably do it well.
I have thoughts on that. You cannot realize U1 symmetric Haar random unitaries in very low depth. I think some of these results on like hardness of recognizing phases still go through.
Log n depth, or you have to
I think so, but that's not proven. That's just intuition. I think so.
About the short range correlation.
The short range correlations. So say like I could also apply the same thing to like just a product state, so with only short range correlations, and I could scramble it under this low depth circuit. And it would be impossible to tell that original state had only short range correlations. Yeah.
It's a still happen, you have the scrambling all of those.
Yeah, as long as the scrambling is over a depth just bigger than log n. Yeah. Still just above log n, yeah. Okay, so I'd like to close with an open question on this and then just some more broader open questions. So what I've just told you is a kind of surprising and like seemingly very wrong fact that the phase of matter of a quantum state is hard to learn. Because we have tons of daily experience and like the whole history of physics of very easily detecting the phase of matter of very complicated quantum states. So somehow in the real world, pseudo-random phases of matter do not seem to be appearing, or at least they're not ubiquitous. And this is despite the fact, again, that real world systems, we believe, are like highly complex and messy. And they also have fairly large correlation lengths. And so an open question that at least I have is what specific property of the Hamiltonians and ground states in the real world guarantees that their phase of matter is very easy to recognize. And I put a kind of parentheses question mark around this because I think from a physics perspective, we already know the answer. And it's related to the renormalization group. So the renormalization group tells us that very simple properties of states kind of scale favorably as we increase the system size. And more complicated, less relevant properties of states become less important as we coarse grain. And there's even, okay, and so this is telling us that the ground states in the real world have some higher structure encoded by the renormalization group beyond just them being connected to a fixed point state by some depth of circuit.
Isn't translation symmetry maybe more fundamental in terms of our recognition that facilitates?
But as I said, we have these results on low depth translation invariant symmetric circuits where all of the same hardness arguments go through. So I think it's not translation invariance.
The unit still has to still be extended.
That's true. That's true. So maybe, yeah. That's fair. Yeah.
The unit still has to be extended, not very extended.
Yeah. So our translation invariant circuits, they use the same brickwork construction. So the unit cell is like polylog-n. So maybe.
Maybe translation at the very microscopic level is helping us.
Maybe.
Because basis is kind
yeah.
of uniform in some sense.
Yeah, that could be possible. My feeling is somehow it's not essential and that ideas from the renormalization group are more fundamental. And even like Ethan and Shankar and Sunwon have a paper that shows that with very, very mild assumptions that sort of imply that the renormalization group holds, then they provided an algorithm to efficiently recognize the phase. But I think from that's some good physics intuition, but from a more rigorous quantum information standpoint, understanding exactly what conditions on a Hamiltonian imply that, these simple structures emerge, I think is kind of an open question. Yeah.
I guess it's also widely local Hamiltonia, at least the gap.
Yeah.
Area low entanglement, which I guess will not be true for these random states.
Yeah, so these states will have area times a log factor entanglement. So maybe that's some hint of a difference. Yeah. Okay, because I'm running over time, let me just close with a few other open questions. Okay, so the take-home message again of most of what I've talked about today is that quantum circuits can appear very random and complex at much shorter depths than our naive intuition would have made us expect. And some kind of broad sets of open questions that this raises that I'm interested in if people want to discuss. So one is, do our results, which are on basically random circuits on qubits, how do these extend to things like bosonic or fermionic or even Hamiltonian systems? So where, say in a Hamiltonian system, where might the randomness come from? And at what time scales or depths does random behavior emerge? So I think, there could be interesting connections here between like projected ensembles, which I think Wenwei will tell us about later this week. And for fermionic systems, there could be very important applications to things like match gate shadows, so classical shadows for fermionic states. A second open question is trying to kind of like make this phase recognition question a little more concrete. So the counter examples of phases we construct involve applying a low depth circuit to a fixed point state. But in so doing, the kind of parent Hamiltonian of that fixed point state is becoming polylog local. So the states we construct are not ground states of constant local Hamiltonians, they're ground states of kind of polylog local Hamiltonians. So there remains a kind of interesting open question, which is what is the complexity of phase recognition for ground states of constant local Hamiltonians, maybe with large correlation lengths. So maybe that could teach us whether this is easy or hard. And then a final question, which doesn't directly connect with lots of what I've talked about, but I think is important, is if complexity is so easily hidden in ergodic random quantum systems, like I just discussed, where do we expect quantum advantage to come from in many body dynamics? So, there's this huge hope in the field that quantum simulation of quantum systems can lead to large quantum advantages very generically. And a lot of our intuition about that, if you ask people, is that quantum states, and especially states that have been time evolved under some Hamiltonian, become very highly entangled. So they're very complex to represent classically. But there's a long line of ideas, or not a long line, but there's like a number of ideas in many body dynamics, like Tibor's papers are some of the early examples, showing that we can often do very well classically by not even trying to keep track of the complex degrees of freedom of a quantum state and only trying to store some simple information. And I think our results kind of complement this by showing that in these specific random circuits, the complex degrees of freedom are very rapidly hidden from any simple measurement observed. So I think this kind of combination of works raises a very important open question for the field, which is if, ergodic and generic systems so easily hide their complex degrees of freedom, can we find systems that don't do this, where maybe there is some scalable quantum advantage for quantum computers compared to classical simulation? So yeah, that's all I have. Sorry I went over, but thanks for all the questions.
Maybe we shift over lunch. And
Maybe,
people are interested.
okay, yeah, maybe let's do that. Actually, let's do it like lunch.
So you're just going to announce that then.
Right.